All right, good news about set two for E&M is that it should be relatively similar to set one, so at least it shouldn't be as long, but let's just go ahead and get this over with. Calculate the absolute value of the electric flux through the Gaussian surface on the zero equipotential line. It's still Q enclosed over epsilon naught. Yeah, Q enclosed over epsilon naught. So that's going to equal, it's 1 nanocoulomb, so 1 over 8.85 times 10 to the third when you take those scientific notation. Yeah, I guess let's go ahead and calculate it. I want to be complete with this, I guess. So multiply that by 10 to the third, and you get 113 newtons times meters squared per coulombs. All right. Okay. All right. That's it for that page. Let's move on to the next one. Another work done stuff, going from C to E, E to D, D to A, and then calculate the approximate magnitude of the electric field. So same sort of a thing from the first one. Let's go back to the picture then. All right, where are D and E? D and E are along the same equipotential. And then you're going from D to A, which is a change of -10 for your potential. Okay, so if you're going from C to E is a change of -20. Change of -20. So what you should get from E to D, you should still have 0 work done because there's no change of potential. And then from D to A, you should have half as much work done compared to C to E because you have half the potential difference then. There we go. Similar to set one again. Calculate the approximate magnitude of the electric field. Yeah, same sort of a deal from last time. Let's approximate it by delta V over delta X. And that's at what, position B? So, oh, that's fun. All right. Let's take that point right there. Let's take this point right here. That's a change of 1, 2, 3, 0.5-ish tick marks. 3.5-ish tick marks is about a distance of 1.4 meters. So delta V over delta X, negative, and then absolute value, right, for the electric field. So then the change in potential between those 2 points is +10. So you end up with absolute value of 10 over 1.4. I'm not going to use fractions this time. I'm jumping straight to my calculator because I'm ready to be done with these. 7.14 newtons per coulomb, approximate for the electric field at point B. All right, let's move on. All right, the positive test charge is released at position C, and you're trying to determine the direction of the net electric field force and then justify. Let's go ahead and clear all of this. So point C, it should still be normal to the equipotential, much like in set one. Since the rod has uniform density and the sphere has positive, however, this time it's going to be pointed down in the negative y direction. Okay, so this is so much nicer because I already have an idea as to how to solve these now. Same reasoning as the first one. The test charge repels from the sphere and attracts to the rod. And the electric force field / force at C must be normal to the equipotential surface. All right, there we go. Let's move on. If you guys can't tell, I'm definitely ready to be done with these, but I do want to solve all of them just so you guys can see. And I don't know, I guess it's a good mental exercise to keep me sharp for 3 hours. All right, the sphere and the test charge are then removed, and you want to use integral calculus to derive the electric field potential where point P is above the rod then. All right, Vp equals K integral dq over r, which is K integral lambda dr over r, where your distance between point P and the rod is going to vary from the distance between them, right? The distance between the top edge to point P, which is yp over 2L, minus 2L, to just yp, which is the distance from the bottom to point P. negative sign because it's a negatively charged rod. So you get negative k lambda natural log of r from your bounds. And therefore, you're going to get negative k natural log of the thing that they want you to derive then when you plug in your bounds. There you go. All right, sketch a y component of the electric field. It is going to be a negative electric field now, but this looks similar to the last problem, so I'm not going to bother taking the derivative. It's going to be a concave down function that approaches infinity as you approach to L, and that approaches 0 as you get really far away. Yeah, there we go. All right. Okay, it's going to be like a 1 over r squared relationship, essentially. So, okay. All right, move on to the circuit question. Wow, we solved that one actually pretty quickly. So, okay, now you're trying to find something that increases with time. You're trying to measure something that increases with time to determine R. Well, it sure is not going to be the voltage across the inductor. So the two resistors are identical. So let's actually just go ahead and measure the voltage across both of them together. That'll probably be the easiest thing. You could measure it across one resistor separately if you wanted to. I want to measure it across both of them together because we know that the voltage across the inductor in steady state should be 0 then. So therefore, the voltage across both resistors together should equal the battery voltage. Describe a procedure that can be used to graphically determine. So start recording data with the voltmeter as you close the switch. Once the voltage reaches battery voltage E, stop recording data. All right, there you go. Yeah, and then after that you can graph as well. All right. Okay, cool. So what should happen with the voltage across the resistors then? Well, they should go something like it should start at 0 and then approach the battery voltage. So it should actually be something like E and then 1 minus E to the negative t over time constant then. So what I still want to do is if I wanted to get something that would give me a nice straight line, I would still need to plot like natural log of something. So I would get V of R over E, right? Natural log of that should equal 1 minus E to the negative t over tau, not that, sorry. Natural log of that minus 1 minus that, sorry. Natural log of 1 minus that fraction should give you negative t over tau. Yeah, there you go. Okay. Yeah, that's fine. All right. So let's go ahead and plot negative natural log of 1 minus V of R over E. And then on the y-axis, on the x-axis, let's just go ahead and plot t, right? So then if you plot that, you should get a y-intercept of 0, and this should just be a straight line then. So cool, right? How would you use that information? The slope is going to equal 1 over time constant, which is going to be equal to the time constant is L over R, so that's going to equal REQ over L, which should actually then tell you that the slope multiplied by L should actually equal 2R because they're in series. So R should equal L times the slope over 2 then. Yeah, cool. And I think actually, and some of you probably pointed this out in the comments, I can't even remember at this point, but I think in set 1, I actually said that that R should just be the slope times L. It should actually be 2 times the slope times L because of equivalent resistance. So that was my bad. Thank you for those who have pointed it out if you have. At this point, I am actually recording these all back to back, so it'll kind of just depend on, I guess, which one you watch and if you watch them all back to back before commenting. But you do have to account for the fact that it's equivalent resistance in order to get a closed loop. So cool. All right. Move on to the next one, right? Start with Kirchhoff's law, blah, 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 derive a differential equation for current as a function of time. All right. E minus I times 2R minus L di dt is equal to 0. Awesome. There you go. There's your differential equation. Yeah, cool. Yeah, I don't know what else we need to do there. So after reaching steady state, the potential difference across RA is equal to delta V1, and then you replace it with an inductor of non-negligible resistance, and then you get a new potential difference across RA. How should that compare? It should be less than. The reason I know it should be less than is because you're going to have higher equivalent resistance, right? Lower current through everything. Since V is equal to IR, right, the voltage across resistor A is going to be less than voltage that it was before you had the inductor in there as well. All right, higher REQ, and I guess if I want to be complete, it should be because the inductor is in series with everything. Sure. All right. I don't know if they actually care about that. They're definitely going to want you to say that equivalent resistance rises and therefore that lowers the current, and then talk about how that lowers the potential. But I guess we'll just be complete and say it's because it's in series. All right, cool. Let's move on to the question. Oh, geez, I hate this. All right, you have your another magnetism question. Yeah, boundaries. Okay. So region 1 is as wide as your wire, right? And then region 2 is 1.5 times the width of your wire. And you have double the magnetic field in region 2 compared to region 1. So this is going to be fun. All right. Okay. So how does all of that flux end up changing? Let me grab actually, no, I don't need to grab my paper copy again. We should just be able to reason through this. All right, so from 0 to D, no change in flux, obviously, there's no field. From D to 2D, it's going to vary linearly with X because the flux is going to depend on area. Area depends on X. So let me just go ahead and draw that out. All of these fluxes should be positive in this case because all of the field is pointing out of the page then. All right, now between 2D and 3D is where I'm not 100% sure. That's something not 100% sure, meaning I need to work that out, right? And then between 3D and 3.5D, it's constant because you're not changing any of the field through the wire. 3.5 to 4.5D, it's going to decrease at twice the rate then. So let me just write that down. So between that, it should be constant, and then this should decrease at twice the original rate compared to the first rise that we saw, because you're decreasing the flux twice as fast then. All right, so from 2D to 3D, when point S is going from 2D to 3D, what is happening there? Well, you're actually just doubling the magnetic. Oh, okay, it's just a linear increase still, because you're just changing the flux to be twice as much as it would have been otherwise. Yeah, that's actually pretty easy. So there you go. Constant goes down twice as fast. Yeah, that's super easy, actually. Since you're changing the field from B to 2B gradually, just like you changed it from 0 to B gradually, and flux is proportional to field, it should all just increase at a steady rate from 0 to 3, from D to 3D then. All right, so when the thing reaches 1.5D, calculate the direction of the induced current. Well, you're increasing the flux out of the page, so you're going to have a clockwise current in this case. Yeah, opposite reason, or same reason as you had counterclockwise in the other. A clockwise induced current generates a magnetic flux into the page, counteracting the increase in flux out of the page. by Lenz's law. Cool. Derive an expression for the induced current at that point. That's not bad because you just do the same thing, right? Faraday's law is equal to magnitude of induced voltage over resistance, right? So that's going to equal magnitude d phi dt over r. Magnetic field is not changing, so you get b over r integral dA dt. So you're going to get b d v over r then. Yeah, there you go. Because a is equal to d times x, right? And then dA dt is going to equal d times v then, because it's dx dt. Okay, perfect. Derive an expression for the power dissipated. Nice. I squared times r. So that's b squared, d squared, v squared over r. Man, these really are much simpler now that I've gone through the first set. All right. Vertical boundary is now shifted to the right, and you are trying to figure out the total energy dissipated and how that's going to change. So let's go back to the graph. I like to do that so I can see how the flux is going to change. So here's what we had originally again. And if we go over to our new picture, then the flux from 2D to 3 to 2.5D now is actually going to be constant in your new situation. So if I can change my text color. So in your new situation, you're going to have a constant flux from 2D to 2.5D, and then it is actually going to increase from 2.5D to 3.5D. Whoops. Similar to what we had in the original case then. So you'll have that. And then, yeah, and then after that, the field is going to change at the same rate. So you're actually going to have the same energy dissipated. You're going to have the same energy dissipated in this case because the graphs are almost identical. It's just you're rearranging a few sections of this then. So yeah, so what you're having is that the magnetic flux changes for the same at the same rate for the same amounts of time, though not at the same times as in the original case. So you have the same same power dissipated for the same period of time, therefore same energy dissipation. Cool. All right, now you've got a cool triangle again, and you're asked to sketch the induced current. So we got to figure out how flux is going to change. So how is flux going to change in this triangle situation? And then we're finally all done with these. New wires connected. Okay, so what's happening is originally, like right when point S actually gets in the field, you're having actually kind of like a trapezoid shape containing the field, right? As you get as that triangle gets farther into the field, you get a bigger trapezoid, and the bases are actually decreasing, whereas the height, one of the bases is decreasing, whereas the height of the trapezoid is actually increasing. So your field is constant, right? So d phi dt is still going to equal b times dA dt, but now you have the area of the trapezoid to deal with. So you've got b times d dt. We can take out the 1/2 from area of a trapezoid, and then you're going to have base 1, which is constant, plus base 2 times height. So you're going to get b over 2 d dt base 2 times height then. All right. Well, height is kind of like x for your trapezoid here. So let's replace height with x. So the question then is, how does base 2 actually change as time goes on? Because you're going to get b over 2. Actually, no, let's wait to do that. So base 2 is the left base of this trapezoid that I've been drawing on this triangle. We want to figure out how that's going to change with x. So when half of the trapezoid is in, would it not just be equal to d minus x? Yeah, it is d minus x. Okay, easy. All right. Takes a little bit of geometry, but the base is actually just d minus x then. So you get d minus x times x, right? Or b over 2. I'm going to get rid of that. I don't care about that anymore. So you're going to get d dt of dx minus x squared, which is going to give you dv minus 2xv. All right, so it's going to be a straight line, and it's going to be decreasing. So when x is equal to d, wait, that gives you a negative current. Shoot. I did something wrong here. d over 2? 2d? I don't know. In any case, I know that you get some sort of like straight little line. Once the okay. So once the triangle gets to 2D, you should actually have no induced current because you're no longer changing the flux then. So it should just be something along the lines of this. I don't really care about the specifics. But the base, the left-hand base of the trapezoid here is going to depend linearly on x somehow. The height is also going to depend on x, and frankly, my interest in this problem has begun to wane at this point. I just know that it should be like a decreasing current because you're increasing the area by less as the triangle moves through, and then once you get point S to 2D, you're no longer increasing the flux through the surface, so you have zero induced current. All right, we're done. Yeah, sorry about the lack of enthusiasm right here. I don't know. These questions got kind of long. I did actually kind of like I kind of liked a few of these questions. Like the mechanics questions were pretty nice. Yeah, I didn't really find them too bad once I understood what the rotation question was asking. But I actually kind of like the air resistance one. It was super quick. You didn't do too much with it, I guess, but the energy and momentum question, although tedious, that one's pretty nice as well too. And the tension, how does the tension change in both of those rotation questions? That was kind of a nice little thought exercise, I guess, too. So yeah, but next year we have a different exam format. I'm hoping that the questions will be a little bit less tedious or maybe a little bit shorter. I really did just feel like the Z&M questions dragged on. They were very long. But maybe that's just because I kind of struggled to think about them at first. Anyway, as usual, just let me know if you don't agree with anything that I've done for my work here. Let me know if you want some clarification, and I'll be happy to give some clarification to you or explain my thought process a little bit more. But thanks for watching, and have a great rest of your day.